All right, so the first set of practice problems, we're going to go back and use some of those bar graphs that you saw in the lab, only now you are going to be drawing them yourself. So let's talk a little bit about this. All right, so the situation shown below. Ooh, this did some weird formatting stuff when I saved it. That's really weird. This is supposed to be each situation shown below. You're going to list the objects in the system within the circle. So we're going to walk you through this in a minute. But remember to always include the Earth's gravitational field. Okay, that should say field. In your system. All right, the Earth has to be in your system. On the physical diagram, you're going to indicate where your zero height is, or what we call our reference point. And then you're going to sketch the energy bar graphs for position A. That's going to be our initial bar graph for our beginning energy. And then this is going to be our final or ending energy snapshot. Okay, obviously the cart's going to keep moving through the loop. But these are the two snapshots we're going to look at. Okay, our initial and our final. And then we're going to write a qualitative. Qualitative means that there's no numbers. Okay. We're going to write a qualitative equation for our energy that indicates the initial, if we transferred anything in or transferred anything out, and the final energy of the system. Okay. So I do not know why the belows, that is so strange. Okay. Well, in the situation shown below, a spring launches a roller coaster cart from rest on a frictionless track into a vertical loop. So assume the system consists of the cart, the earth, the track, and the spring. So they're telling you what to put in your system. So I'm going to go ahead and do that. The cart, the spring, the track, and the earth. Ooh, that was hard to fit in there with my stylus. Okay, so all four of those things are inside our system. Okay, and then step 2 up here said to indicate the choice for zero height. So traditionally, we usually just use the ground or the lowest point here that the object will be at. So this is what I'm going to use for my zero height. Okay, that means at position A, it's going to have zero height. At position B, obviously, it's going to be at a position that is not a height of 0. Okay, so we're going to go through our little checklist that I talked about before. We have to go through our checklist so we can figure out what energy we think is there. Okay, so initially, the roller coaster is at rest. So at rest means it has a velocity of 0. It means it has a kinetic energy of 0. We just said it's at our 0 reference point. That means it has a gravitational potential energy of 0. Okay, we do have a compressed spring, all right, because that spring is compressed. We know that because it's going to launch the roller coaster. The only way it can launch the roller coaster if it was compressed before. So we draw a bar chart. I use all the lines that are here. I just think it's easier. And it gives us our total energy here. Okay, so we have 1, 2, 3, 4, 5 boxes of total energy here. Okay. Now we talked about the law of conservation of energy. It says whatever total energy I start with, I have to have the same amount at the end unless something is transferring energy into the system or out of the system. Well, we have a frictionless track and everything is inside the system. So there's no work being done on this system. Okay. This velocity over here, we should label as an initial. This height over here, we should have labeled it here. The initial height of the cart is 0. Okay. All right. Now the spring launches it. That means at position B, it's not even in contact with the spring anymore. The spring is no longer compressed, so it has zero elastic potential energy. The frictionless track tells us we have zero dissipated energy. The reason the dissipated energy shows up on the right-hand side, but we don't see it at all on the left-hand side, is because we can't dissipate any energy until we actually start having some sort of energy transformations going on in our system. And at the initial position here, we don't have much going on yet, so we can't have any dissipated energy yet, okay? All right, is it moving up at the top? Heck yeah, it is. So that final velocity does not equal zero. Is it at a height above the reference point? Yes, it is. So it's going to have kinetic and it's going to have gravitational potential energy. I had 5 boxes of energy to start with, so I have to have 5 total boxes of energy to end with. I'm going to split their energies up half and half. We saw this in the energy lab. So this is 1, 2, 3, 4, and then my 2 halves here make up my 5. So as long as I have the same total boxes that I had before, then I have a conservation of energy situation, okay? An equally as valid bar chart would have been to do 4 over here. So now I have 1, 2, 3, 4 boxes. And I do 1, 2, 3, 4 here. 1, 2, 3, 4 boxes here. So now I have not violated conservation of energy. I have the same total amount of energy before, however much each of these boxes is worth. And I have the same total energy afterwards. All right, our last step is our conservation of energy equation. That comes from our diagram. So I look at my first diagram. I didn't have any kinetic. I didn't have any any gravitational potential energy. I had all elastic. So my total energy on the left-hand side of the equation is going to be just my elastic potential energy. Well, the law of conservation of energy says the total amount of energy has to equal the total amount of energy at the end. So at the end, we're going to look at our second energy bar chart. I had no elastic potential energy and no dissipated energy. I had kinetic and gravitational. So my total on the right-hand side is kinetic energy plus gravitational potential energy. So again, this is just coming from the diagram, okay? So let's look at 1B. Repeat the problem for a frictionless system. So we still have a frictionless system, so let's go ahead and X out the E dissipated. And you could X it out up here too. I don't care where. I ask that you exit out so that I know you know it's not there. Kind of like we did on the graphs where we put zeros on there instead of leaving it blank. You can leave these blank because that is a little different than before, but I usually tell you to exit out so you don't have to worry about it, okay? Now our system is the cart, the earth, and the track, okay? So it's the cart, the earth, and the track. But it's not the spring. So the spring is an outsider now. So everything inside is our system. Everything outside is not our system. My height here, or my reference point, is going to be the ground that the cart is on and that the spring is on. Okay, we are starting with the cart, but no spring, okay? That means it's not moving here, so its initial velocity is equal to 0. Its initial height is equal to 0. So I have no kinetic energy. I have no gravitational, so you can either exit at the bottom or exit out of the top. But now my spring is not part of this system, so I do not have any elastic potential energy at the beginning. The spring is going to do work to transfer energy into our system, okay? So now the force from that spring is going to do energy on our system to transfer it in that energy, okay? So however many bars I decide that the spring added in is how many bars of energy I should have on the other side. I'm trying to make that look like an arrow, but I didn't do a very good job. So if I transfer in 1, 2, 3, 4 boxes of energy, that means I still have the same track and the same cart as before. So we said we were going to go ahead and divvy it up half and half. So 2 boxes go to kinetic, 2 boxes go to gravitational. My equation is the work done by the spring, so I usually put that kind of down here as a subscript, is going to equal the kinetic energy plus the gravitational potential energy. So the right-hand side of my equation looks exactly as it did above. The only thing that changed was now the spring was outside the system and it had to add energy in through work instead of the object or the system having that potential energy to start with. All right, part C, same system, but assume that there's friction between the cart and the track. So now we have friction. So now we're going to have some dissipated energy. I'm going to go ahead and do a preemptive 1 box of dissipated energy. Can I do 2 boxes? Yes, I can. Can I do 3 or 4 or 5? Yes, you can. But you have to be careful because we still have some other types of energy here. Okay, so we're going to do initial height of 0. Now everything is back in the system, the cart, the spring, the earth, and the track. So cart, spring, earth, track are all inside the system now. So I'm looking at the total picture. So it goes back to looking just like the first one did, where I just had elastic potential energy. I'm going to do 4 boxes because that's what I ended up being consistent with. So 4 boxes here, okay? It is not moving over here, and it does not have a height, so it does not have kinetic or gravitational. It's just got elastic. So the left-hand side of my equation is just elastic. All right, I gave that dissipated energy 1 box. This height here is the exact same height as it was here. It's the exact same height as it was here. So it should still have the exact same gravitational potential energy that it had in the previous 2 situations. There's no spring with the cart here, so the spring energy is gone. So now I have 1, 2, 3. That means I have less kinetic here now that we have friction. Well, you saw that in the skateboarder lab, okay? So that means now I have kinetic energy on the right-hand side plus gravitational potential energy plus I have now the dissipated energy, okay? So again, these equations are coming right from the diagrams, and I'm just writing what's there, much like we did with the sum of the force equations. You could kind of think of these as sum of the energy equations. And by sum, I mean the total of them added together, okay? The sum of those. All right. Hopefully this helps. Couple of things on the practice when you get here. They're changing it up a little bit. So make sure you're paying attention to what's going on. I always forget to change these. The Y is the height. Okay. So when it says Y, that really should have said height. And then 3A does have it as the height. And then it has the velocities. The person, you can relabel one of those as E person or E chemical because it is a chemical reaction in their muscles that helps them push things. So you can use that for the person and just change one of the energies in the bar chart. That's fine. Okay. Let's see. We have heights there. We got the bungee cord. Make sure you're reading what they're telling you to put in the system. Okay. They're telling you what to put in the system. Be careful over here. Same thing. Watch your systems. Okay. And what happens. Just like I showed you the example when you transfer energy in, work can also transfer energy out. So keep that in mind, okay? And look at how I did it to transfer energy in and think about how you might do that to transfer energy out, okay? I hope this helps. You will have a quiz over this the next class period. It's going to be some basic stuff on with energy bar charts. So make sure if you have questions, you ask them before the quiz. Remember, quizzes will close at 11:59 p.m. The day that they are assigned. Okay, so you only have till the end of the day to get those done. All right. Alrighty, have a great rest of your day.